Okay, so yesterday we talked about writing equations of polynomial functions given their zeros. So we're just going to kind of keep running with that topic here and talk a little bit more about some things with the zeros. So we talked about that a zero, if we have a zero, then essentially what we also have is a factor, okay? Because for any zero, let's say the zero was k, then x minus k must be a factor, right? So we can take all the zeros of a function and we can put them together and have all the factors and then find this equation for a polynomial, any given polynomial with whatever zeros that it is. And so we talked about complex zeros and how if 1 plus 2i was a 0, then 1 minus 2i must be a 0 also. Okay, so just to kind of recap a couple of those things. So what I want to talk to you today is some more ways to use the zeros to help us analyze or write equations and maybe even look at the graphs and see what happens, okay? All right, so the first thing I want to talk about is multiplicity, and you have to kind of think back when we were talking about multiplicity. Multiplicity just simply tells us how many times a factor is repeated. How many times a factor is repeated. So if I had, if I told you that 5 was a 0 with multiplicity of 3, well then what that would tell me is that x minus 5, because remember if this is a 0, x minus the 0 is the factor. So x minus 5 actually occurs 3 different times, okay? And so we talked about that with multiplicity, and what we also talked about, and again I'm just reviewing just a little bit before I introduce the kind of new stuff here, is we talked about even versus odd multiplicity, okay? And we said when it's even multiplicity, that means that it kind of bounces off of the x-axis. It never actually crosses through, it just kind of bounces off. But yet odd multiplicity is going to go straight through, okay, whatever it does, it's going to go straight through that x-axis for odd multiplicity, okay? So in the case of this one, of multiplicity of 3, then at the value of 5, 1, 2, 3, 4, 5, whatever else the function is doing, it's going straight through this one way or the other, but it's going straight through that value of 5, okay? So just to recap on multiplicity. Now, what if I asked you to write the equation of a function with the following zeros? Let's say I told you that it had zeros of 2, multiplicity 3, and -1 that has a multiplicity of, we'll say 1. Okay, essentially what this means is I've got my zeros, but these are repeated solutions, right? This one's repeated 3 times, this one's repeated 1 time. So whenever I need to write the actual equation, I need to say, okay, well, x minus 2, because it's x minus my 0, to the 3rd power, right? Because it happens 3 times. And x plus 1, this one's to the 1st power, right? So what happens is this becomes a problem that I have to literally write out 3 times here. I've still got my x plus 1. And remember, as I'm multiplying, I really don't want to multiply more than 2 at a time. So I am going to take my first 2 here, and I am just going to distribute through. So that would be x squared minus 2x minus 2x plus 4. Okay, again, I'm still just working with just these first two, and I'll expand and simplify to that third one in just a minute. So now I have x squared minus 4x minus, or plus 4, excuse me, and 2 that I'm going to multiply by x plus 1. Okay? Now, again, with the multiplying, x squared times x is x to the third. X squared times 1 is x squared. Minus 4x squared minus 4x plus 4x plus 4. Okay, and again, just kind of clean it up a little bit. Get your like terms together. X to the third minus 3x squared. Oh, those cancel. That's nice. Plus 4. Okay, so when given multiplicity, there's what we do. All right, moving on. If you have a graph, and let's say my graph, let's say that I told you that you had a 0 of -2, multiplicity 3, and 1, multiplicity 4. And this time I'm matching up a graph to what would serve these conditions well. Okay, so here's what you have to think about. As I look at the graph, I'm looking for one that goes through -2. Because that multiplicity is odd, it's going to go straight through 2. But at 1, with the even multiplicity, it's going to bounce around, right? So maybe it looks something like this. Okay, if that actually came up and touched the axis there. All right, so as we match up, we're just kind of looking for things along those lines. All right, going back to when we talked about yesterday with the fundamental theorem. Okay, that fundamental theorem told us, I'm going to say fundamental theorem of algebra. It told us that the degree is the number of solutions, the number of zeros, right? So if I give you an equation, let's say x squared minus 2x plus 7, okay? To determine the number of real and complex zeros I have, so here's what I need to do. I know that my total number of zeros is going to be 2, right? So to find out how many real and imaginary I have, what I'm going to do is I'm going to actually graph this. Let's see if I can get my calculator to come up here without being frozen. So I'm going to graph this equation. So I have x squared minus 2x plus 7. Delete all this. I didn't realize that was on there. I'm going to do a zoom 6. And clearly I can see that there are no real zeros, right? So what I'm going to do is say for real, there are none because it's not crossing the x-axis any, which means that my imaginary solutions are going to have to be 2. Okay, and so we can employ this method on finding the number of zeros for any equation. So remember, when we're looking up how many zeros, we want to use the degree for the total, and then the graph on your calculator tells you how many real. And then, of course, whatever's left must be your imaginary solutions, okay? How many imaginary zeros? All right, moving on. Yesterday we talked about linear factorization and completely factoring a polynomial. And so I want to talk to you about that just a little bit more. If let's do this. Let's find all zeros given a complex zero. Because here's where it gets a little bit harder, okay? Now, what we did before and on your last test is that given a zero, we found all the other zeros. But here we're going to be given a complex zero, so you have to remember, it is key to remember that when you have a zero, you also have a factor, right? And I say that all the time, but to have one is to have the other, and so you have to make that connection between the two. So let's say that I have this equation. Let's say I have f of x equals 4x to the fourth plus 17x squared plus 14x plus 65. And I told you that x equals 1 minus 2I is one of the zeros. How might you find all the other zeros? Okay, so the first thing we're going to do is, given a complex zero, the very first thing we're going to do is we're going to divide by the zero given. Don't let it intimidate you because it has an imaginary part. We're going to follow the same suit that we've done before. Remember, if you have a zero, you have a factor. And when you divide by a factor, it gives you the other factor. So what we're going to do is we're going to divide synthetically, of course, because we're talking about x minus a number, right, for that factor. All right, so we're going to divide synthetically. But instead of it just being a single number, it's going to be a complex number. So outside, we're going to have 1 minus 2I. And inside, we're going to have, now remember this placeholder here, I don't have a power of 3. So I'm going to have 4, 0, 17, 14, 65. Okay, here we go. So drop down the first. And again, don't get caught up with how bad this looks, because the reality of it is, it's what you've already done. It's just going to be a little more complicated as you do it, okay? Multiply around. So the 4's got to multiply to both of these pieces, so it's 4 minus 8I, right? When I add this together, I get 4 minus 8I. Now, here's where you get into a lot more work. What I need to do is I need to multiply here, right? But this becomes a FOIL problem. So I have 1 minus 2I times 4 minus 8I. And I know that it looks like I am never going to get a remainder of 0, but hold tight because we will. 1 times 4 is 4, minus 8I, minus 8I, plus 16I squared. Remember, an I squared means change the sign of the number. So I get, this is going to be minus 16. So I get negative 12 minus 16I. Okay? Negative 12 minus 16I. Combine the real number portions here. So 17 and negative 12 is 5 minus 16I. Okay? All over again. I'm going to change my color so you can see here. 1 minus 2I times 5 minus 16I. Okay. I'm going to FOIL out, and I would get 5 minus 16I minus 10i plus 32i squared. Again, this becomes negative 32, and this simplifies down to negative 27 minus 26i. So negative 27 minus 26i. When I add these columns together, I get negative 13 minus 26i. All right, one more to do. Again, I know that this is a lot, but stay with me. Multiply. Okay, so again, I'm going to just FOIL this out over here on the side. So I've got 1 minus 2i times negative 13 minus 26i. So I get negative 13 minus 26i plus 26i plus 2 times 20, that'd be 52 I squared, which becomes negative 52. These cancel, and look what I'm left with, negative 65. Now, I do all that to show you that it's the zero, right? But it's not doing me any good with all these i's to find the other zero. Remember, that was what I needed to do, was to find the other zero. So what I'm going to have to do is I'm going to have to divide by the conjugate, because remember yesterday we said if 1 minus 2i is a 0, then guess what? 1 plus 2i must be 2. I can hear y'all groaning from here as you think about having to divide this again, but we are going to need to, because the whole point, remember, this is my remainder, my constant, my x squared, my x to the third. And as I go through this, there's really no way for me to get this into a factorable enough form that I would be able to actually find the other zeros. So I'm going to have to divide by 1 plus 2i to see if I can get this broken down a little bit further. Now, the nice thing is, remember, if it's a factor of the whole big polynomial, then it's also a factor of each of the factors, right? So what I'm going to do is I'm going to divide by the conjugate, but I am actually going to use what I just got whenever I divided. Okay, so here's what we're going to do, and this is, make sure you write this down because this is where it gets a little sticky, okay? I'm going to divide by 1 plus 2i, but I'm not going to divide all of these this time, okay? I'm going to divide by 4 minus 8i, 5 minus 16i, negative 13 minus 26i. Okay? All right, so we divide by the factor, and then we take that value and we divide by the conjugate there. All right, so I have 4. And you're going to see quickly that this is not quite as nasty as what the other was. And I get, whenever I multiply through here, I get 4 plus 8i, right? Well, 4 minus 8i plus 4 plus 8i would just give me 8. These would cancel, right? Because I'm just adding here. All right, so I multiply around again. So again, that 8's got to multiply to everything. So I do 8 times 1, which is 8. And then I do 8 times 2i, which is 16i. And you see what's going on here. How nice is that? So 5 and 8 is 13. Again, around. And I get 13 plus 26i, which gives me 0 as it should because it's a factor. So now look at what we have to do. So now we've got these two complex zeros, right? We know what they are. They are 1 minus 2i, which was given to me in the beginning, 1 plus 2i, and whenever I factored that just now, I found out, remember the bottom of that synthetic was 4, 8, and 13, which tells me that 4x squared plus 13x plus 8 is also a factor. Okay, so now what I'm going to do, these don't have any x's in them, I'm good, right? Those are zeros. So now what I want to do is I want to say, okay, well, when does this equal 0? Okay, so I think this is step 3. So we're going to set all factors to 0 and solve. Okay, which we've already done here, and we've already done here because those are already the zeros. So now we just need to set this equal to 0 to solve. So of course I'm going to try to factor first. 4 times 8 is 32. What multiplies to 32 but adds to 13? Nothing multiplies there. So what I have to do is, because it's a quadratic, the quadratic formula, which is, remember, opposite b plus or minus the square root of b squared minus 4ac all over 2a. So I have negative 13 plus or minus square root of 13 squared minus 4 times a times c all over 2a. And I get negative 13 plus or minus the square root of, so now I'm just going to plug this in, 13 squared minus 4 times 4 times 8, 41. Is that 13 squared minus 4 times 4 times... Did I copy this right? I don't think I did. I got these mixed up, y'all. This should have been 8x and 13. I am so sorry. We're just going to roll with it and pretend like this was what it was. The whole point of the matter is that you take the quadratic, you set it equal to 0, and you solve it, okay? Even if that means you have to do so in quadratic formula, that's fine too. So here are your other two zeros, okay? So the point, and I do apologize for getting those terms mixed up, but the point here is that once you get it factored down, set equal to 0, then you continue solving for your pieces, okay? And you continue to find those zeros. So if I needed to write these by the zeros, okay, and this one would be negative 13 plus the square root of 41 over 8 and negative 13 minus the square root of 41 over 8. Remember, factors would be x minus this. I'm going to just put a little extra set of parentheses in here. X minus this one. And then you have your other two zeros that we started with. And this is just if we needed to put it back in standard form. Remember, it was 1 minus 2i. And it was 1 plus 2i. Okay, so this is my linear factorization form. Again, If I hadn't mixed these terms up, it would probably make a lot more sense on that part for you. But get it down, take your quadratic formula portion, break it up into the plus or the minus, and then write the equation. All right, I think that's enough for today. We will finish up. We will pick up actually with 2-6 tomorrow, okay? So y'all have a great day. I will see you tomorrow. I'm going to leave your homework assignment. Actually, let me just put it on here so you know, and then I will leave it with the substitute for tomorrow also. So we'll do page 215. So remember, yesterday you had 1 through 12, and that's due on Wednesday. So for tomorrow, you're going to be page 215. You're going to do numbers 13 through 26 all. Okay, and these are just, these are not that bad at all. You'll get into the ones that are a little more hard, or a little bit harder whenever you hit 33. And we'll just go through 36, and that'll be it on those. I think that'll do it. All right, y'all have a good day, and I will see you tomorrow.